So I want to prove one result about Weyl restriction of scalars. Okay, so let's consider schemes like this. And one define a functor. So let me write pi, because it's easier to write and to read than calligraphic R. So the restriction of scalar from Z to S of Y is defined by, for any scheme T over S. So we say that the points with value in this functor. So this is the same as the Z morphism from T cross Z into Y. Okay, so by definition, this Weyl restriction is a right adjoint to the Bates change functor from S to Z. So we have this property. So it's a functor. We will see that in some cases it is a scheme, but it's easy to, so that's an easy remark that in any case, this functor is a sheaf for the FPQC topology, which means that if we have a morphism which is an FPQC covering map, then the usual sequence is exact. That is the T points of our functor are exactly those T prime points which have the same images in T double prime, where, as usual, the double prime means T T prime cross T prime. And then this sequence, then the sequence below is exact, which means that the first map is injective and its image is exactly those elements here which have the same images. And the reason is simply because, so this, by this property, so this is the same thing as Z of T cross S Y. And so this is Z of T prime cross Z Y. And here this is Z of T double prime cross Z Y. Okay, and the map from, so let's call this T prime Z. Well, and so this map is still FPQC cover. And the last one, so this is the same as T prime. Okay, so if this one is a FPQC covering, then it is a universal epimorphism. And so this one is also a universal epimorphism. And since this one is the same as the fiber product of two copies of this one over that one, so we know that this is, the bottom row is exact. Okay. Hence, the bottom row is exact. Okay, so this is an easy observation, but it is useful because to prove, now we have seen in August that when we know that a functor is a sheaf for FPQC topology, to check representability, this can be done FPQC locally. That is okay. So yes, that's yes. This is what is done in the book by Bosch. Hmm? Yes, 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 yes. Yeah. So if we call this P, for example, yeah. So it is sometimes denoted. I think, yeah, something like this star file. But in SDA3, this notation is used. Mm-hmm. This one, yeah. So yeah, but you're right. It's a some direct image in some sense. Okay, so now we introduce some definition. We say that the scheme Z over S is essentially free if there exists an open, as a risky open, yeah, an open covering. So we can by some SIs. And so these are fine open subsets. And over each SI, there is some, and so let's say that this map is affine and faithfully flat. Such that if we call Z prime I equal to the inverse image of this one, so this one is covered by open affine. So Z prime ij for some j's, such that each coordinate ring is a projective module over O SC prime. Okay, so, well, so that's the definition. And let us just give an example. So let H be S group, S empty, a group of multiplicative type over S, then precisely then H is essentially free over S, because as a definition of multiplicative type, we know that there exists a covering of S by open affines, and over each SI a map which is affine and faithfully flat, such that actually H over SI prime becomes isomorphic to some diagonalizable group with M an abelian group. And so in this case, we do not need the second set of indices, because then we have directly that the ring, then the coordinate rings. So this is just the coordinate rings of S prime. So it is a group algebra of M over this one. And so this is already free. This is already free as OSI prime module. Okay, so groups of multiplicative type are examples of schemes that are essentially free over the base. And we are going to use this property to prove the following theorem. So this is number 25. So assume Z over S is essentially free. And that Y is a closed subscheme. So that is that the map from Y to Z is a closed immersion. And then the result is that then this restriction of scalar functor is represented by a closed subscheme C of S. Okay, so let's prove this in several steps. So the first step, okay. So just to make notation shorter, so let us denote by F this functor. And the proof has 4 steps. So the first step is assume that S itself is affine, and then is also affine with B, a projective A module. Okay, so this morphism corresponds to a morphism of ring of A into B, and we assume that this makes B into a projective A module. And so, since this is a projective, so there exists. Okay, so one has. So we can, as A module, since B is projective, it is a direct summand into some free A module. And so this is a direct sum over some index set. Okay, so this is just as A modules. And so we can consider the coordinate dual forms. Okay, and so let's phi lambda from L to A be the coordinate forms. Okay, so this is just so this is the A linear map that takes an element in there to the lambda to its lambda coordinate. Okay. And by assumption, Y is a closed subscheme of Z. So let's J is the ideal of B, defining Y. And okay, and let's E be a set of generators of this ideal. And let I be the ideal of A. So A corresponds to the base scheme S generated by the coordinates, the phi lambda of X, for X running through this set of generators, and lambda over this. And the claim is that then F is represented by the closed subscheme C, which is just the spectrum of A over I. So this is what we are going to prove. Okay, we just take a set of generators. We look at the coordinates in some basis, and so this is the ideal that will define the thing. And so why is that? So let us prove this. Proof. Okay, so let T2S be a morphism, so be such that the natural map from yt to zt is an isomorphism. Okay, so let me write it here. That is, let us consider a morphism from T to this. Okay, because we saw the other day is that giving a morphism a T point of this functor is the same thing as a morphism from T to S, such that the pullbacks over T become isomorphic. So let's take such a point and let further, and just to make the proof very clear, and let T prime be here and some open affine in T. And so we can write, so this is the spectrum of some, how do I want to call it? Okay, so let's consider this situation. Okay, then of course, so this is preserved. Then we also have that the pullback to T prime is still an isomorphism. But now everything is affine. And so we have a ring homomorphism F from the ring A, which corresponds to S, to R, such that the natural map so we have this inclusion from Y to Z. So this corresponds to the map from B to B over J. And pulling back to T prime means we are making tensor product. So that this natural map is an isomorphism. Okay, so this is the case. So this is the case. This is the case. Well, if and only if so any element in any element in J, of course, is 0 in this quotient. So this is the case if and only if the image of X tensor 1 in B tensor R is 0 for all X in E. Because so an element X in E, it goes into this ring to X tensor 1, and it has to be 0 because of this isomorphism. So this is a condition. And okay. Yeah. No, in this one, because it is obviously 0 here. Yeah, so it means that the image in there is already 0. Okay. And so this is equivalent to say that the image in the free module is 0. Okay, since B is a direct summon in this free module. But now what is the image here? So if we write, if one writes that the given X, which is in B, so if we write it as an element of the larger module L, so if we write it as so in this basis, so these are the coefficients with, so the coordinates are in A. The image of X tensor 1 in L tensor over O. So what is this image? Well, so we're making tensor product over this map. And so this is the sum of all lambda of the basis element E lambda tensored. And it is F of phi. And so we see that this is 0 if and only if F of phi lambda of X is 0 in R. So which means that and so this has to be true for all X and all lambda. And so this statement precise is equivalent to saying that I, which is the ideal generated by those things. So this is that I is contained in the kernel of F. And so this is equivalent to saying that the morphism from T prime, which is a spec of R, to S, which was spectrum of A. So it factors through the spectrum of A over I. Okay, so we see that the condition is precisely that the map from T prime to S factors through this closed subscheme. Okay, so and here T prime was an arbitrary open affine in T. And so, well, I restricted to the affine case to make the proof clearer, but we get that the map T2S factors through this subscheme C, so which is the closed subscheme of S defined by I. So this completes the proof in the first case. So this is okay. So okay in case where S and Z is spectrum of B with B projective A module. Okay, so this is the basic case and the main idea, and the rest of the proof is well is just obvious details to go to the general case. And okay, so let me just do the second step. So we still assume that S is affine. And now we assume that Z is covered by open by affine open ZI. Should I give a name? Oh, let me write ZJ. So this is spec of some PJ with each BJ projective A module. Okay, so what do we do? So we consider the intersection of Y with those BJ. So this is defined by an ideal G index J of Bj, and we get by the previous, and so we get by step one. Yep, you're right. Spec Zj. I called it Zj. And we get by one some ideal Ij of A. Okay. Okay, so now let's consider a morphism T2S and the corresponding morphism, the corresponding and so I claim that this one, so this one is an isomorphism. If and only if each okay, so if I intersect by the various open subsets, so if and only if these ones are okay, because so we just have a Zariski covering of that, and now this one. So this one here for fixed this one for a fixed J is an isomorphism if and only if the morphism factors through the closed subscheme defined by the ideal Ij. And so we get the conclusion that Yt to Zt is an isomorphism if and only if this is true for all of this, or if and only if T to S factors T to S, sorry, factors through for the intersection of this closed subscheme. So which is a subscheme defined by the ideal. Okay, so this works also in this case. And okay, so the third step is still S affine. And there exists a morphism S prime to S, which is affine and faithfully flat, such that Z prime is covered by affine open subsets Zij such that blah blah blah, just like before. Okay. Okay, so this is slightly more general than the previous step, but what we can say is that so sets let denote by f prime this Bates change to the then by the second step by a closed subscheme C prime of S prime. Okay, because over S prime, we have the condition that we previously had for S. And so the putback is represented by some closed subscheme of S prime. But F prime, it comes from a functor F defined over S, And so by an argument that we used already, so this means that C prime has a distant datum that is an isomorphism of S double prime schemes between the two pullbacks. So we have a scheme over S prime, and so we pull back to S double prime, and we have the two pullbacks. And since the functor comes from S, we have some decent data. And since C prime goes into S prime is a closed immersion, the descent datum is effective. Okay, so this is in SDA1 expo 8 corollary 1. So yeah. Actually, it's true more generally if you have a scheme over S prime, which is affine, and so which is the case in particular for closed immersion. And C prime comes from a closed subscheme C of S. And again, by an argument that we used already, and since F is FPQC sheaf, then C represents F. Okay, so we are done in this case, and the fourth step is similar. And so the general case is that S is covered by SIs with SI and affine open subsets. And each SI satisfies the assumption of 3. And so this implies that if we denote, if we put Fi with the restriction of F over Si, so this is represented by a closed subscheme Ci of Si, and again by the same argument, the Ci's glue to a closed subscheme C of S. Okay, so it's basically the same argument. Where this map is replaced by the map from the disjoint union of the open Si to S. So okay, and so you see that in 3 and 4 we use the facts that I proved at the beginning, that this functor is a FPQC sheaf, and so representability can be checked locally. Okay, so we have this nice result. And what are we going to do with this? And I'm going to prove two propositions. Okay, so again, let S be the Bayes scheme. And I need a lot of schemes, so let us call G, Y, X, U, B, S schemes with one of them, which is U, essentially ray over S. And we have the following proposition, which is 26.1. And consider, let's call P the product of G cross S over U. And let's consider a morphism A from P to X be some S morphism. And let V be a closed subscheme of X. And finally, let P prime is the inverse image of, so we have, okay, so we have V, which is a closed subscheme here, and I denote by P prime the fiber product. So P prime is P cross X with V. Okay, and so since V is a closed subscheme, so this is a closed subscheme of P. And the claim is that and so let G prime be the subfunctor, the subfunctor of G, such that for every S scheme T, so G prime of T is a set of those G in G of T, such that let me be this. Well, so let me put, so let's say that, so G of U is contained in V. So, and so formally, this means that the morphism, and so in more formal terms, so this means that if I consider the morphism A composed with G tensor the identity of U, So this is a morphism that goes from T cross U to X, because G cross the identity. So this takes these schemes to G cross U, and then A takes it into X, and we want this to factor through the subscheme P. Okay. So this is the formal definition. And so this looks mysterious, but the statement is that then G prime is nothing but the restriction of scalars from P to G of P prime. And so this is represented by a closed subscheme of G. Okay, so let us prove this. So first there is one lemma, an easy lemma that I should have said at the very beginning. If we have a morphism which is essentially free, then for any base change, ZT over T is essentially free. Okay, so let us check that we have our hypothesis. Okay, so we have P is G cross S U, and so we project to G, and so this is essentially free because U is assumed to be essentially free, and we use this lemma, and it contains this one, so which is a closed subscheme. And so by the theorem, we do have that the restriction of scalar from, so the previous Z to S is now replaced by P to G, and the previous Y is replaced by P prime. And so this one is represented by a closed subscheme G prime of G. Well, and now if we think about what this means, so a T point of this and for any T to G. So the trick is now that the base scheme is a G, and for any T over G, so let us call this functor F. So what is F of T? So this is one. this is a one-point functor. If the pullback, if PT, if the inclusion is an isomorphism, and it is the empty set otherwise. And the condition that the inclusion P prime T into PT is an equality. So this means precisely that the morphism from T cross U going by G cross identity to G cross U. And yeah. Yeah, so I'm just trying to say is that this equality precisely means that this map factors through V, because well, if one thinks well, one has to think a little bit, and I'm too tired to think now. But if you think over it, this is exactly this. Okay, because yeah, no, actually, this is because P prime is exactly the subscheme such that this morphism lands into V. Okay, so and so we do have this. Okay, so this is representable, and if you think about the definition of this functor, this means exactly that it consists of those T points of G such that the map factors through V. And now we are happy because this gives a familiar result. So this was very general, but of course we are going to translate this in more familiar terms. And the consequences is now a G is a S group scheme acting on a S scheme X. So we have a map, an action map like this. And let U, V be subschemes of X. And we can consider the functor. We can consider a subfunctor, which I denote by transporter, and I underline to mean that it is a functor. So the transporter in G, so this is the sum factor of G, such that for any S scheme T, so the value, so these are just those G in G of T, such that G of UT is contained in VT. Okay, because, well, so we have a map GT cross T over UT. So this is a subscheme of this. And so we have the action map from GT cross T to XT. And so it makes sense to consider the set of those T points of G, which map UT into VT. So this is the definition of the transporter. And so this corresponds exactly to this case. And so this is represented by a closed subscheme of G. Okay, so this is the subscheme of those G which take U into V, and we do not claim equality here, and so we define also the strict transporter, that trans strict. So this is the same. So this is those G in G of T such that G induce an isomorphism between the two. And so this is also representable because this is this intersection. And so this one is also representable. Okay, because so if tau denotes the map of G which takes G to G inverse, so the strict transporter is a set of those G which transport U into V and such that the inverse transport V into U. So the strict transporter is also representable by a closed subscheme. And okay, so let's say that, so this was the first point. So the transporters are representables. So are the strict transporters. And now probably the most interesting case. Yeah, I forgot the assumption. Here the hypothesis was that U is essentially free. So I should not forget this hypothesis. If U is essentially free over S, and here this is true if U and V are essentially free over S. If U is equal to V and is essentially free over S, then the strict transporter of U into U, this is what is usually denoted the normalizer of U into G is represented by a closed subgroup scheme of G. Okay, because when U is equal to V, it is clear that this subfunctor is in fact a subgroup functor, and so it is represented by a subgroup scheme. And finally, the fourth assertion is that if H is a closed, is a subgroup, is a subgroup scheme of G, which is of multiplicative type, then the normalizer is, sorry, H, represented by a closed subgroup scheme of G. Because, as I said at the very beginning, a group of multiplicative type is a basic example of scheme which is essentially free. Okay, so now we know that the normalizer of a subgroup of multiplicative type in a group is represented by a closed subgroup scheme. Okay, and so I think it's a good time to stop here. And in the next lecture tomorrow, I will do the same for centralizers instead of normalizers. Okay, so let me just say just one word about how this goes. So these are, so here we are talking about transporters, that is functors that carry a subscheme into another subscheme. And so this gives rise to transporter normalizers. Now, instead of and so what we will see tomorrow, so here we have the situation where we have two subschemes of X, and tomorrow we will have a scheme Y, and instead of subscheme U and V, we will have two morphisms. Okay, so, and G is acting on X. And now we can consider the sum factor of G, which transports the morphism U into V. But then transporting the morphism is a pointwise equality instead of just moving one subscheme into another. And so there is a similar result for the transporter of a morphism into another morphism. And this gives, as a special case, the centralizers of a morphism. And if the morphism is the closed immersion corresponding to a subgroup, we obtain the centralizer of the subgroup. Okay, so this is a small variation on this proposition, and we will see this tomorrow. Yep. Yes, sure. Yeah. But so this is a nice case where it is representable. Yeah, because they are equal to their own normalizer, and then it's another argument. Yeah, there is another. Yeah, so this is another general result of Grothendieck. No, I think that you have another idea in mind, because of course, if the group is equal to its own normalizer, it is representable. But the result is that then the quotient exists. So this is a result of Grothendieck, that if you have a subgroup scheme equal to its own normalizer, then you can form the homogeneous space. Okay, so this is another result. Okay, so tomorrow centralizers, and next week reductive groups.